calculus, a little bit more implicit differentiation for you. 213 notes. Let's see, implicit differentiation we just did. We're going to just see some more unusual kinds of problems in this one, but same basic ideas of the one we just did on 212. So hopefully you tried that worksheet, check your answers, see how you're doing with that, and we can go on to a little bit more complicated problems here. So let's see, remember, find dy dx. If it is not an x, it gets, well, why is everything moving around? If it's not an x, it gets a d variable dx with it, a dy dx. Okay. All right. Now this one's a little bit more complicated than it seems. Um, Before I go on, remember, um, two questions are going to come up during this one. Make sure you answer those for your points. All right. Let's see. So we were saying cosine xy equals 2y. Well, this cosine xy is a problem. That's the complicated part of this one. And the 2y shouldn't be, but this cosine xy. Let's see. Something is going to be equal to 2 dy dx over there. Well, that's the easy part. Let's see what we can do with cosine xy. Here's what I see. We have a trig function. Inside the trig function is xy. Something is inside. That means we're going to use a chain rule on this one. Okay, that's normal. We've done chain rule before. Trig function before angle. Xy, though, x times y, is a product rule. When we do that derivative, this gets interesting. A lot of fun, isn't it? Well, let's see. Trig function before angle. So I'm going to start way over here and say cosine gives us negative sine of, we can do this with colors here, inside xy, keep it the same, xy, multiplied by the derivative of the inside. That derivative is a product rule, so I'm going to put it in its own little brackets here. That is derivative times original plus original times derivative of y, dy dx. That is the product rule. Equals 2 dy dx. Told you these get a little bit more complicated. So if you can follow the rules, though, you should have no problem kind of thinking through these. All right. How do we solve for dy dx? We have one over here with the 2. One is inside these brackets, this x dy dx term, or that's all one term together. Inside the brackets, though, so just think about what would happen if this wasn't trig, if it was just something else. You would distribute. Well, that's what we're going to do here, too. To get that dy dx out, we have to distribute. So the next piece on this one, all of this term will get distributed inside here. And there are 2 terms here. So what that looks like is we're going to multiply negative sine xy times y. That y does not multiply the angle. That is always protected. So this is negative y sine xy plus x dy dx multiplies here. So we're going to get negative on this one. Negative x dy dx sine of xy. You can put those in any order you want, as long as you don't put this x dy dx in the angle. That's fine. That is all one term. Equals 2 dy dx. It does not matter how the terms are made up. We're going to do the same process. We're going to get the dy dx terms on the same side, factor it out, and divide. That's all we're going to do. It doesn't matter how complicated it is in there. There's trig functions, there's xy inside. It's all just math pieces, okay? So shouldn't matter what it looks like. So let's keep this one here, negative y sine xy equals, let's keep the 2 dy dx, add on x dy dx sine xy, all of that, factor out. We have left 2 plus x sine xy. Gotta have a big parentheses there. And divide that off. Or this equals negative y sine xy divided by 2 plus x sine xy. There is our answer. dy dx is, I have negative y sine xy over 2 plus x sine xy. Can't cancel anything because this plus 2 makes it two terms on the bottom. That's it. Remember, it could be positive on top and both negative on the bottom. Either way works. Okay. So even though they're complicated pieces, we can follow all the derivative rules as we go through that. You have to be willing to accept these weird answers that we're getting over here. They're just kind of complicated combinations. All right, number 2. Find dy dt. Now this is different. If you remember what we did last year with this, let's just follow the rules from what we said before. All the others before had dx on the bottom. Well, dx, the whole idea was take every derivative with respect to x, so x variables were fine, everything else got this little description of the derivative. Well, this t means with respect to the t variable, which does not exist over here. So if nothing is a t variable, every variable gets compared to t. So all variables get a d variable dt attached to them. We've got to compare all of them to t. This is a little look ahead to some word problems we're going to do where t is time. That has an application to it. But basically, if it's a t or any variable that's not here, every variable is going to get its own little derivative description chain rule or fraction with it. Okay, so let's go through that here. Start with the xy. Remember, this is a product rule, derivative original, original derivative. We end up with 1y plus x dy dx, right? No, we're doing a dt, so don't get carried away too soon. All right, let's try that again. What's the derivative of x? We said 1, but that 1 needs a dx variable compared to t. So this is dx dt times the original y plus the original x times dy dt. The derivative of y is dy dt. So there is our product rule. Okay, every variable is going to have this little fraction. Notice these fractions are different. They are different variables. There are 4 variables in this little part of the equation. Regular x's and y's, derivative x's compared to t, and derivative y's compared to t. Okay, a little bit more complicated. Keep going here. 2x squared minus 4x. But don't forget, compare the x to t. dx dt equals 3 is gone. That's our 0. Don't write it down. 5y is plus 5, and it's a y gets dy. Remember, we're comparing to dt. So this fraction, find dy dt, the denominator is the important part to tell you what fractions do you need to include or what you are comparing everything to. Now, when it says find dy dt, that is a variable. We find it here and we find it over here. That's the variable you're going to solve for. Okay? So that's the one to get alone. Remember how I said there were 4 variables here? There's 4 variables in this whole equation, 4 different variables. Solve for one of them. All the others will be on the other side. So let's get those terms together, factor it out, and divide. So this term and this term are the ones we want to get together. So over on the left, we'll keep, I'm going to write it y dx dt. Kind of put the dx dt last, I guess. Minus 4x dx dt equals 5 dy dt minus x dy dt. Factor that out. 5 minus x. And divide by that. Let's see, y dx dt minus 4x dx dt is over here. Divide by 5 minus x. Divide by 5 minus x. Gone. So we end up with dy dt equals Now we have y dx dt minus 4x dx dt, all divided by 5 minus x. That's our answer. This dx dt, we said it was a fraction before. It is, but this is not considered a complex fraction. Dx dt is a variable. So it's y times the derivative of x variable minus 4x times the derivative of x variable. You can factor that out if you want and write it in front. That would be okay. But this is okay for an answer. You don't have to worry about what's looking like a complex answer on this one. So that's what happens when we switch these variables around. The denominator variable tells you what to compare everything to. And you might have a whole bunch of different fraction variables throughout the problem. All right, 3. This, if you remember, that is the full symbol, like F double prime, 2 on top, 2 on bottom. They're in weird places. But this is the second derivative. There we go. Second derivative for this. We can do second derivatives. We've done them before. Do the derivative once, look at the answer, do the derivative again. So let's do the first derivative, dy dx. Okay, this says we're going to do this derivative twice, comparing it to x twice. It's kind of weird. It's two different positions. All right, let's do the first derivative, y cubed. 3y squared, it's a y dy, we're comparing it to, in this case, x. Minus 3x compared to x, we're good. Equals 0 plus y is dy dx. Now, before I just jump into the next derivative, simplify. Okay, so let's do it this way. 3y squared dy dx minus dy dx, and add that 3 to the other side. Factor it out. 3y squared minus 1 equals 3. So divide by 3y squared minus 1. dy dx is 3 over 3y squared minus 1. Now, do this derivative. That's going to be the d2y over dx squared. That's our second derivative. But how do we do this side? Now, maybe it's fortunate we only have one variable here. But this is just going to use regular rules. In fact, if we want to rewrite this, 3 times this to the negative 1, that's be okay. 3y squared minus 1. If you want to do it that way, you can use a chain rule here. Doesn't matter what variable's inside. We now know how to handle every variable. So let's go up here and do another one. So the d2y over dx squared, the second derivative comparing y to always comparing to x, is, let's do the chain rule one. That'd be negative 3. So the negative 2, keep the 3y squared minus 1. Remember, that's the original. No dy dt, dx is in there. Times derivative 6y dy dx. Okay. We were doing the second derivative. We got a first derivative variable in there. That's okay. It's just another variable. It's just written in a weird way. All right. So we're pretty much solved for d2y over dx squared, the second derivative, but we should clean it up here. 6y and negative 3. We've got negative 18y dy dx, and if you want to, times the negative 2 or over 3y squared minus 1 squared, if you like that better. Not a complex fraction anymore. Okay, we don't have to worry about simplifying that. But that is our second derivative. The second derivative includes the first derivative. Now, there's one more piece with this. Because the second derivative includes the first derivative, we don't really like that. Okay, we like it in terms of x and y. That's what it says up here. Not in terms of x and y and dy dx. Only variables allowed are x and y. So guess what we get to do? Along the way, we found dy dx. We can use either one of these. Okay, let's use this one. That can substitute in. So the last piece we're going to substitute. So this is the second derivative, d2y over dx squared. is negative 18y over 3y squared minus 1 squared. But up here, instead of dy dx, we can put times 3y squared minus 1 to the negative 1. Let's combine these two like terms here. Those parentheses are the same, and we end up with negative, let's say 54y, and this is going to be cubed on the bottom, 3y squared minus 1. That is the second derivative. So, first derivative, then do the second derivative with whatever rule applies. But the second derivative will have a first derivative inside, and you already found it to replace, so you get rid of that variable. Easier with just x's and y's. A little bit trickier problems on here. You can see just examples of things we know how to do if we just slow down and think about it a little bit. So understand what it's asking for. Okay. Now, the bottom part here, let's just make sure we know how to answer these questions. Okay, not from any equation, just describe on this. So look for important words here. Points where y equals 2. Remember, points, original. That's what you have to think of. So where y equals 2, you want to find points like something comma 2. Use the original equation. So we'll just say here, plug a y value of 2 into original. If you plug y in, you'll get the x. So plug y equals 2 into the original. That's what we need to know how to do to solve that one. What about find where the curve crosses the y-axis? Crosses the y-axis is otherwise known as the y-intercept. These aren't all calculus problems. The first one wasn't. Find the y-intercept. So interpret what the words mean. It makes it easier. So find the y-intercept means plug in, the y-intercept always has an x value of 0. Plug in 0 for x. But remember, we have a lot of different equations we've looked at, so we need to be specific. We're finding a point here, so in the original. Okay, the original equation. So know where to plug in. Cross the y-axis, y-intercept. Plug x into the original. Okay. What about find the equation where x equals 2 and find the slope where x equals 2. Should have written a little bit more here. Find the equation, I left out some words, of the tangent line. That's what it should have said. Sorry about that. That's important. Find the equation of the tangent line, the line tangent to the curve, when x equals 2. Find the slope where x equals 3. Okay. I think you have the slope one first, the way I organized them here. So, well, slope is easier. Slope is derivative, so we need to know a dy dx derivative. So find the slope where it equals 3. That's a plug-in. So we have to find dy dx and plug in x equals 3. Now, one thing we need to know about this, though, like what we just did before, if we're doing implicit differentiation, our dy dx usually has two variables. So we'll put down here, we may need to find a y value in the original. Okay, you might need to plug 3 in to get a y value to go with it, so you have enough to plug into the derivative. We'll find the equation of the tangent line. We know how to do that. That was always point and slope. Find a point by plugging in x equals 2. Where? In the original. And slope, we're going to plug in x equals 2 and possibly the y equals from the point into the derivative dy dx. Remember, it's y minus the y value. Fill that in. No, plus little extra string mark there. So y minus y1 equals the slope times x minus the other x value of that point. Okay. So just know where to plug in, and just realize now you might have to plug in both variables, and you always get those from the original equation. I give you x, go to the original, get y. And what about this? Find where the tangent lines are horizontal first. Horizontal means slope is 0, and that means we're going to solve where the dy dx equation equals 0. With a fraction, that's the numerator equals 0. Okay? So what would make it vertical? Vertical slope is, or vertical line slope is undefined. Okay? So how do you make something undefined? Well, we could say, well, dy dx equals undefined. Is that what we do? Well, what makes it undefined? Well, if the horizontal, we usually have a fraction with numerator equals 0, makes a fraction 0. So this one really means denominator equals 0. That's what we do to find the vertical tangent lines. Now, in both of these, you might solve to get 0, and one variable will be solved for. If you need points, you need both. You'll need to go back to the original equation to find the point. So look very carefully. It asks where or find the points, means you need both x and y. Always the original equation to find x and y. And what would you do with this? Find if two tangent lines are parallel. So remember, parallel, we're talking about derivatives here. The whole thing about parallel is same slope. So find if two tangent lines are parallel means do they have the same slope? So we're asking is dy dx at one x value or at one point, let's say at x equals a, the same as the slope, the dy dx at x equals b. You might need the full ordered pair for those back in the original, but that's how we see if two tangent lines are parallel. Do they have the same slope? Okay. If we want to make them parallel, we make the slopes the same. That's the whole idea. So that'll help you through some of the more difficult ones on 213. We'll go over some of these after the quiz up through 210. Remember, that's the next day of CU, the first day back. The second day in our in class is going to be review on these implicit, make sure you're doing the right things, and we'll start the applications for these. These applications can actually go pretty quickly as long as we got this idea down of the dy dx and can change it around a little bit. All right, make sure you are preparing for that. You should have seen also maybe a little homework quiz pop up on Schoology, so you will get an email if that shows up if you haven't seen that already. Okay, little practice for you there before the test. All right, I will see you guys with the test next time. Office hours and stuff. If you have questions, let me know on there. All right, see you.